All right, we're gonna get started with our next video. This is the third spring break review. I'm probably gonna do one more Tuesday or Wednesday of this upcoming week. I'm not sure yet, but please do stay up to date on the channel, and I will keep updating as problems come through my email and through my office hours. Feel free to access those as well, given that we're all online now. All the recitation TAs will have their office hours online, and we'll use those questions that you guys ask during that time to kind of make problems like these so that we can get a better look of where you're at for particularly acid-base chemistry, but also moving on, we get to buffers and we get further into titrations as well. So let's go ahead and start. So I gave you the question: in the equilibrium system described by the reaction below, which statement is true according to Bronsted-Lowry theory? So we know right away we're working with a Bronsted-Lowry acid-base system. We're not working with Lewis. So in this case, Bronsted-Lowry acids and bases donate what? They donate protons. Lewis acids and bases will donate and receive electrons. So in this case, we're dealing with protons. So I gave you guys a chemical equation here. Let's run through each option. We're looking for the true option. PO4 3- is amphoteric. What does amphoteric mean? It means it can act as an acid or a base. So if we have an amphoteric molecule, it has to be able to donate a proton and be able to receive a proton. If we have PO4 3-, if we add an H+, it becomes HPO4 2-. So that can receive a proton, but can PO4 3- phosphate donate a proton? No, it cannot, because there's no H right here. We need some sort of hydrogen or some sort of proton in the front, anywhere in the molecule to be able to donate. In this case, we don't, so PO4 3- is not amphoteric. HPO4 2- and H2O are conjugate pairs. We shouldn't even have to do any work for this one because we know that HPO4 2-, again, it's a weak acid. It has an acidic proton right here to be able to donate, and then H2O. If they're conjugate pairs, they have to have the same chemical makeup. So in this case, PO4 2- and water are not the same chemical makeup, so there's no way they can be conjugate pairs. Same with option C, HPO4 2- and OH-. There is an O and an H, but in this case, the acidic proton is linked to the phosphorus here, and the acidic or the basic proton here is linked to the O. This is a hydroxyl group, so in this case, those are not the same chemical makeup, so you cannot make that assumption. This one, H2O and OH-. What happened from here to here? We lost a proton, right? If we are H2O charge 0 and we lose +1, 0 minus 1 is equal to -1, and then we still have O and H because we lost the proton. So D would be correct. Those are conjugate pairs. Would this be the acid or the base? This would be the acid. This would be the conjugate base, right? Because this donated a proton. Acids always donate protons. And just to make sure we're correct, let's check option E. PO4 3- and H2O both act as bases. Well, that can't be right because we just said that H2O acts as an acid. So E is incorrect. So the correct option here would be D. A good multiple choice question to think about when you're going through Bronsted-Lowry theory, acids and bases. Which of the following is the strongest base? A very good question. What do we notice about these first four molecules? They have minuses. Usually conjugates have minuses or pluses. So these are most likely conjugates of some sort of acid. So let's take a look at what they are the conjugate of. So F-. Something goes to F-. If an acid goes to F- and an acid donates a proton, what would the acid have to be? It'd have to be HF. HF, if we lose a proton, it goes to F-. Again, 0 net charge, and then we lose 1, so we go to a -1 charge. So that one's good. That's option F. G. something going to Cl minus. Very similar to this, it would be HCl. Because we lose this proton, so we go from HCl net 0 charge to Cl minus 1 charge. Again, you can walk through these with me. You can pause the video and do them ahead of time and check your work. But this would be HClO4. Sorry, I got cramped there. Again, HCl4, lose a proton, go to ClO4 3 minus. One last time, NO3 minus would be HNO3. J is interesting. H2O. What molecule that we've seen in acid-base chemistry would give us H2O? H3O plus. Donate a proton, so we're going to lose -1. We have to go to 0. 1, 0, we're good. H3O, lose a proton, go to H2O. The hydronium acid will make water. So which of the following is the strongest base? So which of these is the strongest base? Strongest base has a high or a low Kb. Strong is equal to a high Kb. So if we're looking for a high Kb, we need a low Ka. How do I know that? Well, we have Kw is equal to Ka times Kb. Kw is always the same. It's always 1.00 to the -14th. So if Kb is high, these both can't be high. If Kb goes up, this has to go down. Likewise, if this goes up, this has to go down. So in this case, we're looking for a high Kb, so a low Ka. So if we have a low Ka, does that mean a strong or a weak acid? A weak acid. HCl, strong acid. HCl4, strong acid. Strong acid. Now we're down to F and J. We know if you've done a lot of acid-base chemistry in high school or even Chem 109, you may have seen this come up a number of times. HF is one of the common weak acids. So HF is a weak acid. So if you knew that right away, you could go to option F as your answer. But if you didn't know that right away, we could also look at H3O+. H3O+ going to H2O. H2O really isn't a strong or a weak base. Again, H2O is kind of interesting because it's its own thing. It has its own dissociation. So H2O is almost like a throwout. That wouldn't be correct. So now we're between these four. We would realize that these are all strong acids, and we would get HF as our answer. Because, once again, we're looking for a high Kb relative to a low Ka. It's a good question. That one came up during office hours. A solution has a pOH of 2.45. What is the corresponding concentration of OH minus? Is the solution neutral, acidic, or basic? So right away, we should look and see we have a pOH. I personally don't like to work in pOH because you won't use it in the lab. You'll be using pH. How do we go from pOH to pH? pOH plus pH is equal to 14. Right? Because if we have the pH scale, it's like a number line where 14 is highly basic and 1 is highly acidic. 7, usually what our blood is neutral. So if we're looking for, this is acid, this is base. We're looking for the pH of a 2.45 pOH solution. We already know this term. So 2.45 plus pH is equal to 14. I would subtract the 2.5 over, and I get a pH of 11.55. So the pH is 11.55. We would be probably about, we'll just say right here. So is this solution neutral, acidic, or basic? Well, determining from pH, we know it's here, and we're in the basic side of the pH scale. So that answers that question. What is the corresponding OH minus concentration? For the rest of your time in Chem 110, you also use it in Unit 1 and 2, more like Unit 1 and Organic Chemistry 1 if you take it at UNL. If you see a P, a lowercase p, and then something, P is equal to negative log. So in this case, we have the negative log of OH. So negative log of OH is equal to our POH, which is 2.45. Negative log is just a term, 2.4 is a number. So this would be like the negative log of X is equal to 2.45. X what we're looking for. If you don't know how to do logs, that's fine. I sometimes forget when I'm doing logs how to work them. So I'm going to show you the way I would do it if you don't know how to do logarithmic functions. I would go to your math solver. So again, press math, it's right below alpha. Scroll down to solver. Put your POH in your E1, 2.45. Clear this out, and you have negative log of X. So you have 2.45 is equal to the negative log of X. Don't forget to zero your X, and then you would solve. So you get an X value of 0.0035. So for X value 0.35, we know the negative log of X is equal to 2.45. So this is our concentration of hydroxide. Definitely know how to do this for your upcoming exam in a week and a half. It will be on there more than likely 5 or 6 times. Very common to see pH and POH questions asked on an exam. So be ready for those. This is kind of how you solve them. This is how I would do it. Again, if you're good with logs, feel free to stray away from the math solver. It takes a little more time. If you know logs, you can go ahead and solve that right away. But if you don't, the math solver is also valid. A solution has a pH of 11.28. Calculate POH, H3O plus concentration, and OH minus concentration. So let's calculate the POH first. The first thing we need to do. So pH is equal to 11.28. And we know pH plus POH is equal to 14. So we have 11.28 plus OH is equal to 14. And our POH would be, so 11.28 would be 2.72. pH of 11.28. If we go up to our pH scale, is this neutral, acidic, or basic? Again, we're very close to where we were at last time. Last time 11.55, so we're just left. So we're probably about right here. If we're right there, we're still basic. So now we calculate the POH and we determine that's a basic solution. How do we calculate the OH minus concentration? We do the exact same thing. So 2.72 is equal to negative log of OH minus, or negative log of X. So I pull up my math solver and I would go down, solver, 2.72 is equal to the negative log of X. Zero that out, solve. 0.0019. Equal to 0.0019. Okay, good. Now we do H3O plus. This is where it can kind of tricky. So we know, just like POH, pH is equal to negative log of H plus, right? Again, P just means negative log. H plus is the same thing as H3O plus. So this would be the negative log of H3O plus. These are both the acidic terms. H plus is a proton, acidic proton. H3O plus is the acidic hydronium ion. So in this case, these are the same. So let's pull out our math solver and let's see what we get. If we put 11.28 in on our top, and then we have negative log of X. Zero this out. If you ran this and this came up, error equals domain, you are not wrong. It's just the 11.28, a negative log of a number cannot come out to 11.28. It's mathematically impossible. So this gave us an error. So now we're kind of stuck. We don't really know what to do, but we have one equation, Kw equals Ka times Kb, right? We know Kw, 1.00 times 10 to the negative 14th, is equal to Ka times Kb. Well, we know our Kb, or our basic concentration, is 0.0019, but we don't know our acid. We're looking for the acidic, right? We're looking for H3O+. H3O+ is our acidic character. So I'm just going to divide this over. I'm going to take 1.00 times 10 raised to the negative 14th. I'm going to divide that by our OH, which is 0.0019. And I get A would be 3 times 10 raised to the negative 12. And that's our concentration of H3O+. Does that make sense how I got there? Again, don't be thrown off when you get error. Technically, you're correct. If you ran all this math out and you get an error, that's correct. But you need to realize that Kw is equal to Ka times Kb. You don't always have to have a Ka and a Kb here. This can mean Kw is equal to the acidic character times the basic character. In this case, we had a basic of 0.0019. You can divide and solve for acidic. Another very good question that came up. All right, we got 2 more today. So which of the following is or are not true for a solution at 25 degrees Celsius that has a hydroxide ion concentration of 2.5 × 10⁻⁶ molar? Let's work through each of them. Kw is equal to 1.00 times 10 to the negative 14. Is that true? Yes. It does not matter, so that can't be, because we're looking for the ones that are not true. So this one is true. This always, no matter what situation you have, it's always going to be 1.00 times 10 to the negative 14. There's no changes to Kw. It's always going to stay the same. The solution is acidic. So we have a hydroxide ion concentration equal to 2.5 times 10 to the negative 6th. Well, we know the POH is equal to the negative log of OH minus. So this would equal the negative log of 2.5 times 10 to the negative 6th. Let's run the number and get POH. So if we do the negative log of 2.5 times 10 to the negative 6th, you would get 5.6. This is our POH. So we take 14 minus that to get our pH. So from here, pH would be 14 minus 5.6, and you would get 8.4. So if our pH is 8.4, I would draw out my pH scale. 1 is acidic, 14 is basic, 7 is neutral. I'm right here. I'm basic. So this one's true, but B is a valid answer, right? Because the pH would be 8.4, meaning it's basic. So if we have a pH, so that'd be not true, correct? Yep. So the pH is 8.4, we're basic. This one's true, this one is not true. It is not acidic. So B is one of your 3 answers. The H3O plus is 4 times 10 to the negative 9th molar. Well, let's set up Kw yet again, just like the last problem. 1.00 times 10 raised to the negative 14th is equal to my acidic times basic. Well, we know our basic is 2.5 to 10 to the negative 6th times my acidic, and my acidic would be H3O plus. So let's find what A is equal. I would divide this over. So I would take 1.00 times 10 raised to the negative 14th, and I would divide that by 2.5 times 10 raised to the negative 6th. And you would get an acidic character of 4 times 10 raised to the negative 9th molar. So this one is true. Right? Do you guys see how I got that? 4.0 times 10 to the negative 9th molar. that would make my acidic character true. So far, the only one that we haven't proven, again, Kw, that's true, that's always true. The solution was basic, pH was 8.4, so that's true. H3O plus, that's true. We're looking for the ones that are not true. This one was not true. It was not an acidic solution. 2 of the above are not true. We only have one that's not true. So your answer would be option B is the only one that is not true. Okay, last one for the day. Just kind of going back to the last video. Again, these videos are available for you to watch. Go ahead and reference the last video if you get stuck on this one. Which of the following would be the conjugate acid in the reaction of HPO4 2- mixed with water? So what do you think we're going to have to do for the first step? We're going to have to write out the reaction. HPO4 2- plus water. Which one of these is my acid? Left or right? It's going to be left. This one has an acidic proton. Water does not. So if HPO4 2- is my acid, what does that make water? My base. HPO4 2- donates this proton to water. If that happens, we get PO4 3- or phosphate plus H3O plus. So now let's look for HPO4 2- conjugate. Same chemical makeup, so it's got to be this one. Again, you cannot go from HPO4 2- to H3O plus. It just can't happen. So if this is the acid, what does that make this? My conjugate base, making this my conjugate acid. H3O plus is my conjugate acid. All right, that's it for today. Again, a shorter review. We haven't gotten into buffers yet. We're going to be getting to those shortly after spring break. That's where it kind of can get tricky with titrations. So please keep reviewing. Please be ready for your exam coming up. I know we have spring break this week. There won't be any lectures. I'm going to post one more video just to make sure you guys are okay with everything we're learning. And then you guys have your exam the week after this one. So please keep reviewing, be prepared. It really won't be that bad. I know it's a different format. Taking exam online may be new for some of you, but don't get too stressed about it. Again, feel free to ask me or any other TAs. Your lab TAs as well are open over break for any questions you guys may have. Yeah, thank you for watching these videos. I hope they are valuable for your time. I think they are. I think they will help you very much in the end. Have a great rest of your Sunday.